In this example, we have the vector v, which is comprised of the components 4, 1, and the vector w, which is comprised of the components -2, -3. And we are to calculate and draw both v plus w, v minus w, as well as 2w. We have on the graph already on the right side here demonstrations of both v and w. Note that v, which has a positive 4 first component, or x component, is going horizontally to the right 4, and for the y component of 1, we are going up 1. Note as well that we chose to draw both v and w starting at the origin, but this is only for convenience. We can draw and maneuver v and w to start at any place, but we just need to make sure that the amount that it moves left or right, as well as up or down, is correct according to the components. Again, we only have v and w drawn here, both starting at the origin for convenience. We are also going to draw v plus w, v minus w, and 2w in the same way. But first, let's calculate those. For the vector v plus w, what we need to do to add these two vectors is to add the according components based on the vector addition formula. So if I want v plus w, we will take the first components of each vector, which would be 4 from v, as well as -2 from w, and add those together. That will be my new first component. Then I'll add the second components, so 1 and -3, that will give me my new second component. This now gives me the vector 4 plus -2 is 2, and 1 plus -3 is -2. So that would be v plus w. Next, let's do v minus w, and I will do that in a different color, and we'll also graph it in a moment in a different color. Here I'll do v minus w. And if we want to take the subtraction of these two vectors, we are going to subtract the according components in this particular order. So v minus w means take the first component for v and subtract the first component for w. We'll do the same thing for the second components. 1 minus -3. This overall now gives me 4 minus -2, which is overall 6 for the first component, and 1 minus -3, which is overall 4 for the second component. Thirdly, we have 2w. Now 2w is not a combination of two vectors, this is a scale of the vector w. If we want to take 2w, what we're really doing is taking the scale of 2 and distributing it to the components of w, that being -2 and -3. If I distribute that accordingly to each component here, we will now get the vector 2 times -2, which is -4, as well as 2 times -3, which is -6. This has essentially created a vector that is going in the same direction as w, but is 2 times as long. That's what a scale will do. Well, let's draw these, and we'll draw them on the same plane with v and w. For v plus w, we have 2, -2. If I choose to start that at the origin, again for convenience, that means I'm going to move to the right 2 and down 2. Meaning the terminal point should be in the quadrant 4 here at x and y coordinate 2, -2. So my vector would be represented like this. Starting, again, I choose at the origin, and terminating at point 2, -2. V minus w, I'll draw another color. This is 6, 4. 6, 4, again, if I start this at the origin just like the other vectors, means that I'm going to go to the right 6 and up 4, so I end or terminate at about 6, 4 in quadrant 1. So this vector is going to look like this. Lastly, we have 2w. 2w is -4, -6, so that is going to end up down in quadrant 4, or quadrant 3 rather, if I start from the origin. And you'll note that if I do make a vector starting at the origin and terminating at point -4, -6, that is going to go along W and simply extend beyond W to get to this point down here. That is what the scale of 2 is doing. It is elongating W, but it's still going in the same direction. Now at this point we are done with creating both a combination of the vectors and drawing them. But I'm going to touch upon real quick what the addition and subtraction of vectors can look like when we reorganize this situation. So first I'm going to talk about v plus w. So I will erase v minus w and 2w from my graph for the moment. For v plus w, which is 2 comma -2, we had that if we started that from the origin, that ended up in quadrant 4. And you'll notice that it seems to be emanating out of the middle of vector v and vector w. So it's coming out of the middle of those two vectors. However, when you're adding vectors geometrically, what you can also do is move them around because, as I said earlier, vectors do not need to start at the origin. You can start them anywhere. One way to geometrically think about what v plus w means is that you are walking along the distance of v, or you're walking along the vector of v, and then once you're finished doing that, you then plus w by then walking along the direction of w. But that means that once you've walked along v, you are now at the end point of v, and you now need to turn and go the direction according to w. W is -2 comma -3 for the components. If I draw that vector starting at the terminal point of v, from the terminal point of v, that would be go down 3 and to the left 2. So that means this vector is going to terminate where v plus w results. This is going to be a very common concept when trying to manipulate a situation involving vectors, that you can move them around to suit your needs and to create a figure that may be a little bit more appropriate. Note that these three vectors, when maneuvered around, v plus w and the resultant v plus w, creates a triangle. So we can start to apply some of the concepts we've done in trigonometry to these situations. Note as well that v plus w would also be the same thing as w plus v. And we can demonstrate that geometrically as if you walk along the w vector first, and then once you get to the terminal point of w, you then start to go based on the direction and orientation of v. Meaning from the endpoint of w, we then go, based on v, we go over 4 and up 1. From there, that means that we are going to end up, yet again, at where v plus w results. So, some important things to think about, that you can manipulate and move vectors to create a figure that may be a little bit more appropriate or convenient to work with. This is also something called the parallelogram rule, where if you notice the figure that I created from taking both v and w and then translating copies of w over here and v over here, this figure I created is a parallelogram. The diagonal that goes across the parallelogram here, this is v plus w. But the diagonal that goes the other across this parallelogram, so from the terminal point of v and w, instead of the diagonal that comes from the initial point of v and w, the vector that would go from the two terminal points here, this vector is actually the exact same thing as the subtraction of the two vectors. Specifically, this is the exact same vector as v minus w, which we said earlier was 6, 4, and we graphed it like this. But I can translate v minus w here to be drawn on the diagonal of this parallelogram. And you can notice if you count from the values on the coordinate plane here, for the x values, I'm going from -2 to +4, which is a horizontal distance of 6 movement. And for the y values, I'm going from -3 up to +1. That is a vertical distance of 4. Meaning, the diagonal there is 6, 4, or the same components as v minus w. So another way that we can manipulate these vectors. I don't need to say too much else though about the scale that we did of 2w, as I've already indicated, when you are taking a scale of that vector, that is simply either elongating it, making it shorter, or possibly making it go in the exact opposite direction, if that scale happened to have been a negative.